Just over 200 years ago, Mount Tambora on the island of Sumbawa in present-day Indonesia erupted. The largest and most violent volcanic eruption for all recorded history. Tens of thousands of people nearby died in the immediate aftermath, a tragedy of terrible proportions. But the event impacted the entire world. 150 cubic kilometres of ash and rock were thrown into the atmosphere. Carried on air currents, it reduced the amount of sunlight reaching the Earth's surface across the world. The following year, 1816, is known as the year without a summer. Temperatures in the summer across Europe were the coldest for the period starting 1766 to the present day. It snowed in New York in June. The drop in sunlight precipitated famine across Europe and Asia. The effects of the year without a summer were far-reaching. The paintings of Caspar David Friedrich illustrate how the sky was temporarily changed by the eruption. Aerosolized particulate matter reddened the sky, as we can observe in the same scene painted fewer than 10 years apart. Warm sunsets in the paintings of J.M.W. Turner are thought to be inspired, unwittingly, by the polluted sky of the year without a summer. In fact, many paintings of this time show a characteristic redness in the sky. Lastly, and this is my favourite, Mary Shelley was inspired to write Frankenstein, arguably the first true science fiction novel, while she sheltered from the miserable summer weather in Switzerland. No doubt the gloom of the outside made its way into the text. Events in the past leave traces in the present. Take a walk in the woods, and any old tree you come across will contain a record of the year without a summer. It has been known since the time of the ancient Greeks that a tree carries within it a record of its age. Tree rings. Each ring indicates a year the tree has been alive. A new ring grows each spring. Count the rings and you determine the age of the tree, more or less. This is dendrochronology. Dendro referring to trees and chronology referring to the study of time. The lines demarking rings denote winters, when the tree doesn't grow. The parts between the lines are where the tree has grown each spring and summer. The larger the gap, the more it has grown. The amount of growth is highly dependent on the weather the tree has experienced that period. Abundant rain and sun generate healthy, wide rings, whereas drought or cold generate thin rings. Other factors, like disease, also leave their mark. Every ring, relative to its neighbours, helps us understand the conditions the tree experienced as it grew, way into the past. Conditions like local and global climate patterns, disease, wildfire, volcanic eruptions and, of course, anthropogenic climate change. Records can be overlapped, the tail of one sample placed against the head of another, building a bridge into the past. The rings embedded in wooden artefacts can then be aligned with known patterns. Artefacts that archaeologists have dug from the ground or dredged from the sea are dated with this technique, provided we bear in mind people, in the past just as today, are more than happy to reuse old wood. These are levels 1 and 2 of dendrochronology. The first and most simple analysis of tree rings reveals the tree's age. The second level makes use of the width of rings in overlapping samples to date materials far in the past. This analysis also allows us to understand the climate through time, dendroclimatology. You've probably already guessed where this is going. In the year without a summer, many oak trees in Europe failed to grow, hence there is a missing ring. Other trees across the world could only muster thin rings, their growth stunted by the miserable cold. Tree rings in Europe today bear evidence of an event generations ago in time and antipodal in distance from themselves. In this sense, the eruption and subsequent climate change is a kind of hyper-object, an object too big and distributed across time and space to be encountered directly, only to be known through the things it touches. But tree rings contain even more information than this, just hidden away. In 2012, the scientist Miyake used an even more complex analysis of tree rings to uncover a massive historical spaceborne event. In the year 774, Earth was hit by a tremendous radiation storm, much larger than anything modern scientists have seen. Soon, other events were uncovered, a handful over the last 10,000 years or so. And while the 774 event was the largest, any of these Miyake events today would bring enough charged radiation to the Earth to bring our technology-dependent world to a standstill. And we have no idea what caused this, let alone how to prevent one. What we do know is there's no reason not to expect another Miyake event in the future. Let's look at level 3 dendrochronology and how this discovery was made. A tree grows from the inside out. The rings in the centre are the oldest, encircled each year by the new, and once it is in place, this material isn't going anywhere. So by examining the chemical makeup of each ring, we can see any anomalous or unusual materials laid down that year. Tree rings are not just a pattern or a record of the past, but the rings nearest the centre are literally older than those further out. Miyake was studying the rings of Japanese cedar from the island of Yakushima. It sits off Kyushu, the most southerly of the 4 main islands that comprise Japan. Known for its nearly untouched subtropical evergreen forest, an environment felicitous for dendrochronology, it's no surprise Yakushima is a World Heritage Site. Harvesting samples from live Japanese cedar trees is prohibited, but samples that have been felled in the past are fair game. Japanese cedar. Appropriately enough, its scientific name is Cryptomeria, Latin for hidden parts. Samples of Cryptomeria contain evidence of a huge spike in the amount of an uncommon form of carbon, carbon-14 as it is known, in rings for the years 774 to 775. Similar spikes have been found for the 5 other events. So what is carbon-14 and why is this significant? Nitrogen comprises 75% of the atmosphere by mass. Only a tiny amount is carbon dioxide, a chemical made of carbon and oxygen. Plants metabolize this carbon dioxide through photosynthesis, and one way or another, this carbon is transferred around the food chain. Carbon and nitrogen are very different elements. Carbon by itself is a reactive black solid, while nitrogen is a colourless gas, but both are vital for life in their own ways. They sit next to each other on the periodic table. Simply put, they are nearly identical in their nuclear constituents. The core of any atom, its nucleus, is comprised of roughly equal numbers of neutrons and protons. There is just one more proton in nitrogen than carbon, and yet this single proton causes all the difference between the elements. This is just what distinct elements are. Atoms with different numbers of protons. The upper layers of the atmosphere shield the Earth's surface from a constant but steady stream of radiation from space. Every so often, radiation will hit a nitrogen atom, specifically a proton in the nucleus, and the proton will change into a neutron. As I just mentioned, an element with one fewer proton than nitrogen is carbon, so just as a nitrogen atom dies, a carbon atom is born. But this carbon has an overabundance of neutrons, 2 more than normal. This form of carbon is known as carbon-14, with 14 being the total number of 6 protons and 8 neutrons. The nucleus of the carbon-14 atom is an unhappy alliance, the bonds too weak to hold on to the additional neutrons forever, and for complicated nuclear physical reasons, one of the neutrons will, sooner or later, revert back to being a proton, in a process called nuclear decay, emitting radiation in the process. Hence, it will become nitrogen again. Take a sample of carbon-14, and 6,000 years later, half of it will have decayed back into nitrogen. Normally, the balance between creation and destruction of carbon-14 evens out so there is only a constant, tiny amount of it hanging around in the atmosphere, a sliver compared to the majority carbon-12. All carbon isotopes, as they are known, essentially behave the same. As plants grow, a trace of carbon-14 is absorbed and retained alongside carbon-12, the plant none the wiser. For cedar, when it grows, the material is locked in place. So by measuring the amount of carbon-14 in rings over a population of trees and accounting for nuclear decay, we have a record of how much carbon-14 was in the atmosphere each year. And since the creation of carbon-14 is tied to spaceborne radiation, we have a way of tracking this radiation over the last few millennia. This is how scientists can look in the unlikeliest of places to study the wider universe. The Miyake event of 774 created levels of carbon-14 20 times higher than normal. And these findings are robust, having been corroborated with other cosmogenic nuclide increases, that is to say, isotopes created by space irradiation, with other tree rings around the world and in ice cores. The evidence implies the existence of truly massive radiation storms that have never been seen by modern science, that have no agreed upon explanation. The only plausible source of this radiation is from our local universe, emissions from the sun, or even the explosions of stars at the end of their lives. Let's take a step back. Did anyone see these events happening with their own eyes? And more importantly for us, did they record it? Annus Domini 774. This year the Northumbrians banished their king, Aelred, from York at Eastertide, and chose Ethelred, the son of Mull, for their lord, who reigned 4 winters. This year also appeared in the heavens a red crucifix after sunset. The Mercians and the men of Kent fought at Otford, and wonderful serpents were seen in the land of the South Saxons. Anglo-Saxon Chronicle. The year 774 is well within the historical record. Do we find evidence of such a dramatic meteorological event written down by the record keepers of the time? For instance, in the year 1006, the brightest stellar event in history was recorded across the Islamic world, in China and the Americas. We know today it was a supernova, but then it was recorded as a guest star, visible in the daytime. 50 years later, in 1054, another supernova was recorded by the Japanese, Chinese, and Iraqi civilizations, at least. Today we have photographed their scattered remnants in fantastic detail. However, neither such event registers in the tree ring record. And yet, less than 250 years prior, there are only the faintest historical traces of the Miyake event. In 774, in Britain, there was a single line recorded in the Anglo-Saxon Chronicle. A red crucifix appeared in the sky after sunset. This is the best historical evidence of any of these events. The Anglo-Saxons were the inhabitants of England during the early Middle Ages. They chronicle their handwritten records. As Christians, the appearance of a crucifix was extremely significant. Their understanding of cosmology had Earth at the centre of the universe, orbited by the planets, moon and sun, englobed by the firmament whereupon the stars were fixed. The night sky was a place of eternal and religious truths. Any anomalies in the heavens threatened to disrupt this order. What was it? In 1870, long before the discovery of Miyake events, John Jeremiah, in a paper published in the journal Nature, assumed the crucifix was one of many historical accounts of aurora. Aurora are the manifestation of the solar wind, charged material streaming from the sun, interacting with the Earth's atmosphere. The Earth's magnetic field is generated deep below our feet and emanates into space from the north and south poles. The constant trickle of charged particles from the sun is attracted towards each pole, and 130 kilometers above sea level, it interacts with the atmosphere, causing it to glow. The wavy lines of the aurora reveal the irregularity of the Earth's magnetic field. Aurora borealis in the north and aurora australis in the south happen all the time. Iceland, the northernmost parts of Europe, Russia, Canada or Alaska are far enough north to experience these common, weak aurora from the solar wind. Aurora australis is rarely seen by human eyes, simply as there are few locations close enough to the South Pole from which to observe one. Stronger aurora are rarer, but they do happen. They are the result of occasional eruptions from the Sun, known as coronal mass ejections, CME for short. As it sounds, it is an event where a concentrated blob of mass is ejected from the Sun's upper layer, the corona. Occasionally, they hit the Earth. CMEs are powerful, rare events like a thunderstorm, whereas the solar wind is constant and harmless, like a breeze. The Carrington event, the largest CME ever recorded, caused aurora as far south as 18 degrees above the equator, even further south than Mexico City or Mumbai. These strong aurora glow a deep red, whereas weaker aurora are a wispy green or blue. There are two separate questions we need to ask. Firstly, is John Jeremiah correct when he described the red crucifix as an aurora? And secondly, was it related to the Miyake event of the same year? If it were a Miyake event, and like Jeremiah we imagine it an aurora, we would need to assume the red crucifix is describing a truly massive aurora. In favour of this theory, it was red, as remember, red aurora are the strongest, and a red aurora visible in England would require a truly massive solar event. If we assume this, then the aurora, and therefore the Miyake event itself, would be part of a huge ejection of charged material from the Sun, perhaps lasting a few days or perhaps a much longer period in time. In the Carrington event, the largest CME recorded, the aurora was so bright you could read a newspaper without aid in the middle of the night. We could imagine, depending on the duration of the event, a Miyake aurora being much more striking. On the other hand, the year in question does not align with the Sun's natural 11-year cycle of activity. Every 11 years, the Sun's magnetism reaches a maximum and we see pronounced sunspots and solar flares at this time. The year 774 sits outside of a maxima. However, there are other longer solar cycles which are less well understood. An aurora is a secondary effect of solar activity. If the red crucifix is not an aurora, then it could be the event itself that was witnessed. A supernova, the massive explosion at the end of a large star's life, blasting out radiation for light years in all directions. The observed supernovas in the 11th century mentioned left no detectable trace in the tree ring records. So a hypothesized supernova would need to be much larger or much closer. There are no other records of such an event at the time, so to understand it as a supernova, we can imagine it located apparently near the Sun, harder to see, and hidden behind a huge amount of interstellar dust. The radiation from the explosion, poking out of the dust cloud in 4 points, could lead to its apparent cross shape. If it were a supernova, it doesn't really explain the other Miyake events. Remember, we should hope to find an explanation that ties all 5 or 6 events together. On average, there is just one supernova every 50 years in the entire Milky Way galaxy. The vast majority of these would be too far away to do anything to Earth. The 2 events in the 11th century were coincidentally very close to one another, and in the following 600 years only 2 or 3 other such supernovae were observed. The chances that all Miyake events were supernova, with their tremendous luminance and yet not witnessed, stretches this probability to incredulity. Still, we can't conclusively rule out this specific event. If it were not a Miyake event, we can still ask what the red crucifix was. This improbably suggests there are 2 separate unknown meteorological events in the same year. Suppose this is true. Was the red crucifix the telltale sign of a normal coronal mass ejection? The only description we have leaves a lot to the imagination: size, brightness, duration. The red crucifix could be a small, barely remarkable product of an understood CME. The aurora it caused over-reported, perhaps due to its distinctive shape. More so, maybe it is just a hallucinated phenomenon dreamed up by an Anglo-Saxon after an evening of too much mead. If the red crucifix wasn't even a real thing, it goes without saying it cannot be related to the Miyake event. If the red crucifix was not a manifestation of the Miyake event, that they were separate things that happened to fall in the same year, then what was the Miyake event? Perhaps it was a long-term solar event lasting over a year. In this case, the effect would have been too spread out and diluted to be visible to contemporaneous record keepers. Generally, scientists believe Miyake events are caused by the sun. I'm inclined to agree. Was the red crucifix related? This is somewhat more tenuous, but I do want it to be true, but I also imagine hearsay has played its part. If it were an unusually large ejection of material from the sun, can we predict how big of an effect it would have if it happened today? The most massive radiation storm we have decent scientific records on is the Carrington event of 1859. A massive ejection of material from the sun's surface hit the Earth's atmosphere. Auroras were seen as far south as the Caribbean. Newspapers were readable in the dead of night. Richard Carrington, who the event is now named after, observed a solar flare erupting from sunspots days after a period of extreme auroral activity. But it wasn't until the early 20th century that the Norwegian Christian Birkeland proposed the accepted modern explanation of the aurora borealis, and the sun's strange behaviour was conclusively linked with the ethereal lights in the night sky. At the time of the Carrington event, electrical telegraphy was bleeding-edge technology. A rudimentary network of cables was being constructed to carry Morse code messages to distant parts of the world. The first transatlantic cable had been laid this decade and had just started use when the CME hit. It was extremely disruptive to the network. Electric currents spontaneously formed in wires and operators were electrically shocked, whereas other lines still were temporarily disabled. In 1859, it was little more than an inconvenience, but today an event like this would bring our networked, electricity-dependent world to a standstill. And yet, a Carrington event doesn't even register next to the enormity of the 774 event. If the Miyake event was an even more massive CME, it would be disastrous. Perhaps literally, as the word disaster means bad star. The 774 event generated 12 times the amount of excess carbon-14 to the Carrington event. Events somewhat larger in power than the Carrington event have been tracked by space agencies in recent years, although they have harmlessly missed the Earth. Power grid outages, disruption to GPS and other global navigation satellite systems, high-frequency radio communication outages, satellite damage, and increased radiation exposure at high altitudes are all predicted consequences of another Carrington-like event. The atmosphere would swell, meaning low-orbit satellites would experience more drag, decaying their orbits. Power, internet, and communication will be down for weeks. The world will become a darker and lonelier place, at least temporarily. Much smaller events have knocked out power in Canada and the US over the last handful of decades, and in 2005, GPS communication was knocked out for 10 minutes. It may not seem like much, but I would not want to be in a plane that was about to land during that time. With smaller events, the atmosphere does a great job in shielding us from the brunt of the cosmic radiation. A Carrington event today would incur a massive financial cost. In the US, on the upper end, it could reach $3 trillion, 15% of GDP. Worldwide, this can be extrapolated to over $14 trillion of damage. While the 774 event was roughly 12 times the power of the Carrington event, it probably wouldn't do as much as 12 times the amount of damage, as when something is broken, more damage doesn't really matter. On the more optimistic side, satellites constantly monitor the sun, and any mass of charged material from the sun would take several days to reach us. With this warning, we have time to power down vulnerable systems which aren't otherwise protected. Many critical systems are designed to tolerate big power swings, while others are encaged in metal, insulating them from outside electrical interference. We're not as prepared as we could be, but given larger and more pressing issues, climate change chief among them, it seems unlikely that Carrington-like event mitigation is seen as a priority. Thankfully, the internet is remarkably resilient to disruption, a far cry from easily disruptible supply chains. Technological innovation could help us still, as much as our dependence on it puts us at risk. My point is not to scaremonger. It's still quite unlikely we will experience a large solar flare in the next decade. There are more pressing issues, and in any case we will recover, even at a large cost. We could all do with less screen time anyway. My point is to demonstrate how the natural world is much more interconnected than we sometimes imagine, and our own study of the world should reflect this complexity. Different observations, theories, myths and predictions weave together to form our current understanding of the cosmos, and there is still so much more to learn. This is the first in a series about this very topic, Cosmic Web. Subscribe and look out for it. Thanks so much for watching.